Francisco. So this is a model using a fully 3D dislocation. So this would be what we could do tomorrow afternoon with Coulomb. And what this shows is the contours show vertical, so how much it went up, and then this is 1989, so GPS is just being used at this time for the first time. And so this shows the dislocation, or the horizontal motion. So you see it's pulled in and pushed out, pulled in and pushed out. So this is showing the 3D effect of this finite rupture that's only this length here. But it also shows a little bit of the pattern from the San Francisco earthquake, where the largest displacements are fairly close to the fault, and as you get further away, they go down. But it has that same decay away from the fault. It's just kind of a short earthquake. It was only 7.3, not 7.9, so it doesn't not stretched out as much as the 1906 earthquake. So how do we analyze this? Same idea, edge dislocation, screw dislocation, but now we use edges. And this, we can go into the detail in a bit more, but basically what we can do is we can use the same idea as Thatcher showed, where you just have a single discontinuity that goes to minus infinity. But in this case, it's the edge dislocation going up instead of the screw dislocation going horizontal. But one of the really powerful parts of the dislocations is that we can make it, because it's supposed to go to minus infinity. If you want to have a confined piece of fault that fails, you use one at the top that slips the amount you want here, and then you put another one coplanar below that slips the opposite direction. And so you get a kind of a confined patch of slip. And so that's what this shows. This is the top of one dislocation that would go to minus infinity. This is the top of the second dislocation, also going to minus infinity, with a negative B, which is just the slip. And so down here, B and minus B are counteracting each other, so there's no effect from this part. And we only have this finite source of deformation from here to there, this length lambda. So, and we can, in the case of the dip slip, we calculate the horizontal and the vertical displacements. So here's the main equations that we would use, so we can go back through that. But let's just do Bora Peak first. So here is the model for Bora Peak. So we have one dislocation that would go down to minus infinity, and we need to get rid of the effect of its lower portion. So we put a second dislocation on here that has reverse slip from minus 13 to minus infinity. And so that counteracts the normal slip from this guy down there. So that just gives it this finite piece of fault. And if you look at this displacements that I calculate, it's quite similar to what Bora Peak example was. And so we can do the same. So that's like here, they tried it with the Lister fault, it doesn't work. But when we do it with a straight fault, it works pretty well. So that, compare that with this figure right here. So my arrows that I just calculated would make that line right there. So then the second example would be the Loma Prieta case, so blind fault. So here I have the top of the fault kind of, if you compare this model with these ideas like this one, this is a 3D, oh thanks, 3D view of this here would be more complicated view of my model, but that locked part up there that didn't break would be here. So that's trying to simulate this. Okay? So the last thing that this teaches us is, and this is not now my calculation, this is in the textbook by Stein and Session, so it's a geophysics textbook. They show the same thing. So you can use the same type of dip slip, and if it's a vertical fault, you have kind of symmetric displacements, and you see the depth goes down to about 15 kilometers, and if you go out about 15 kilometers, you kind of get about half of the displacement. So that's what I mean by this rule of thumb. It's just a basic idea or intuition that the depth of the source scales with the wavelength of the deformation. So then you can have this inclined case. So this would be like kind of like the subduction case, where you remember in our little cartoon we saw this patch slip, and it pulls it pulls that GPS receiver back, but it also lifts the seafloor right there. So that's your tsunami-genic displacement right there. Now, here's what happens. You can also have the blind fault, so you can push this down deeper, and you see the effect. It kind of mutes the signal, and that's again an indicator of the depth to the source. So what I've been saying is this kind of size of the source and the depth of the source influences the sharpness of the displacements at the surface. And that's something just you should take away always. Anytime anyone shows you GPS data, GPS velocity, you want to say, okay, do I see any discontinuities? Is it, some deep slip, or is it coseismic, shallow? What can I infer about the geometry of the fault based on this exploration? So here's just the same kind of calculation now, one that I made. So here's a vertical one, and all I do is I pull the bottom down. So here's the displacements for 1 meter of slip with just the shallow. I go to 510. So you see the maximum displacement stays the same, but the width of the displacement increases as I pull the depth down. Here's the changing dip. So this is that subduction case, but tipped on its side. 10 would be this one. So that's like a subduction example. And then here is the buried source. So if you push it down at 5 kilometers deep, actually the peak displacements are away from the fault about 5 kilometers. So again, that depth sensitivity is there. So that's my dip slip story for you guys. So let me just show you, and then I'll go around and help everyone. But what you want to do is you should be able to just do, I don't know how many people know MATLAB, at least a little bit. Okay, not just a little bit. Okay, so it's just a programming environment. So it kind of lets you do a lot of math pretty easily, but also has integrated graphics. And so it has, I'll help you get started, but this is called a script. So it just does all these commands. And all you have to do is just you can change these pieces up in here, but go slowly. And then don't change anything below here. And if I put this percent at the beginning, it's like a comment. So just everything above that is what you would change. So it has the dip is 135. So you can experiment with these. You just change them. Has the B, this is the slip. So 2.5 meters of slip. Okay, Berger's vector is just that term that comes from the mineralogists. Xi upper and zeta upper, these are the where the top of the fault is. And these are in meters. Everything's in meters. So this is the X position is at 0, and then the top is just 1 meter below the surface. Because sometimes if you make it exactly at 0, there's a divide by 0 case. So we need this to be close, but not exactly at the surface. And then you see down dip length is 18,000. So this is 18,000 meters down. And then the X max, X min, this is the width of the study. No, just the width of the calculation. The locking would be this 18. But this is for a dip slip case. So this is remember this more complicated looking equation in here. This is using this math right here.